Okay, let's come to order. Let's see. I've got Green. Hi. How are you doing today? Good. Okay. So let's go over a couple of these. You can keep working quietly on this if you like, but let's hear about A. How did you do? Did you find which ones worked, or how'd you do?
6, -5, and 4, 3 work.
These both work, you say?
Yeah. The third one doesn't work.
This one doesn't work. Okay. Do you guys agree? Company witnesses. Okay. Keep going.
And I got 3 and 4 to
All right. 3, 4 would be another example of a solution. Yeah. Using like the form of the equation to your advantage, just to come up with another one. Yeah. Good. How about the next one, part B? Rachel, what did you come up with on B?
The first one no, and the second two yes.
First one is no, and the other two are yes. Do you guys agree with that?
Yes, sir.
Okay. And then tell me about the. Did you come up with another solution? Did you come up with one?
I did not get there yet.
All right, hurry, get there. We'll come back to you in a second, and you'll give us another solution. That's what's going to happen. Yeah, they don't have to be nice solutions, right? They can be any solutions you want.
0, 4.
She's going to give us another one in a second. Oh, Rachel's got it. I want to hear from Rachel. Rachel, go ahead. Sorry, say it one more time.
-2,
-2, would be another solution. Again, using like the form of the equation to your advantage, you can just like see that that's going to work without even checking it really. If 2 with 0 works. Yeah. Does 1 root 12 work?
Yeah.
Is that right? Someone tell me. Yeah, I don't know.
Oh yeah, that works.
1 comma root 12. We didn't say they had to be nice. 1 root 12 apparently works. Good, good. Plus or minus 1 comma plus or minus root 12 actually, right?
Dang.
That's 4 more points. Okay. Shh. Hi. What about C, Natalie? Where are you? Just kidding. Didn't want to talk to her anyway. Wait. What about who's this? Sabrina. Where are you, Sabrina? Go ahead. For C. Can you solve these? Or one of them? Or how'd you do? Maybe you didn't get there yet. I don't know.
I kind of tried to solve the second one.
Okay. How'd you do? Y equals something.
Said y equals whatever -4x squared plus 16.
4x squared plus 16. Is that what you just said?
-4.
-4x squared plus 16. Okay. And we kind of had a little bit of a conversation about that the other day. Is that good then? This is the same, this describes right here the same set of points as this. Isabel, you have a comment? Plus or minus we need? Do you agree? Okay, you're going to take that change and run with it. All right, so I think that's good. You wrote that on your paper. Good. Keep in mind that, yeah, so this helps us maybe with the plus or minus even answer that second question too. Are there either of these a function? What about A? You didn't take that one? You didn't solve that one for Y? Can we?
Yeah. You can put a plus or minus in front of it if it's a cube root.
I mean, this is a good question. So do it whichever way you like, and then we'll talk about it.
Because I got like.
Go ahead.
I got the cube root of 91 minus x cubed, and it looks like this.
Cool. Okay. Yeah. So the question is that she asked, and I'll just say again, is does this require a plus or minus in front of it? Someone help us. Speak to that question. Go, someone. I hear some people having answers, but go ahead.
No, because if it's negative, then the cube root won't change this.
Yeah, I think I learned this sometime about like odd roots or something versus even something like that, right?
Okay.
So I think we're good, actually. I think we're good, just like that. Which actually is not just kind of a little nuance. It's actually going to be critical in answering this next question. So are these just throw this out there. Are either of these then functions of x? And in fact, in a second we're going to graph them, and that will be a good way to kind of see what's going on. Are either of these functions of x? No, say something.
I think so.
All right. Well, which one or which ones?
I think the first one is
Okay. Why?
because I have no reason not to.
Okay. Proof by default.
Second one does.
Second one, what?
Definitely is.
The second one definitely is. Is that what we said?
Yeah, unless
Why?
I need an NT at the end of it.
Just
Yeah.
justify.
Because if it's that, it has to be a. It's gonna. Oh, it isn't.
Why? Justify.
Maybe it is. I think it's like the circle thing, but a problem.
Circle thing? The second one?
Oh yeah, we didn't even ask what these are yet. What is this for? This one is an ellipse. Do you guys remember that? Okay.
So it doesn't pass it with the line.
That's where it just.
Yeah, this got plus or minus. It's got two parts. So definitely no, actually, is what you meant to say. Yeah, exactly. I got you. I got you. So yeah. But this one, do you agree that this still, we haven't lost any points? Every point that satisfies this is in this equation as well.
That one does work. Yeah, because it can't repeat.
Like there's no point that this describes that this doesn't also describe, right?
Yeah.
So I think this is okay. I think this is a function. And graphing both of these, I've done that for us here. Are you ready? There's part A as the graph of part A, and there's part B, and they're the things that we just this is an ellipse, of course. This first one, I don't know that I would expect you to know what that looks like, you know. Now that you've solved it for y, though, there's no reason you couldn't get this picture on your calculator like someone just showed me a minute ago. Right? So you're welcome to graph this on your calculator. Yeah.
So for B, is there a way to graph plus or minus, or do you have to put it?
You'd have to put it in two different equations in your calculator or something, right? There are some slick ways to do it, but regardless, it's not a one single function of x, right? This first one brings to mind. This first one brings to mind story. Are you ready for story time?
Story time.
Okay. Let me bring the stool over. Okay. Are you ready for story time? Okay. I need a blank screen for this.
How do you write plus or minus on the calculator?
All right. So if you know this story, then don't share because that'd be sad. Okay. This number has a story history. Okay. This is a special number. This is the number 1729, and you're about to learn a little bit of math history. This is actually a true story, unlike other folklore that sometimes isn't true. So there's a famous Indian mathematician named Ramanujan, and he was a genius. He's now dead, but brilliant mathematician responsible for all sorts of important results. And he lived in India, but then he moved for lots of his years to study in the UK with another famous mathematician named G.H. Hardy. And Hardy and Ramanujan worked over the years together. And Ramanujan was brilliant, but he was also very, very sick. And it was on his deathbed that this story takes place. He's laid down in in a bed. He's laying there, and G.H. Hardy comes to visit him in a taxi, and his taxi number, and Hardy's taxi number, was 1729. Okay, and he comes up and he says, just to make conversation, says, I came in a taxi today with the most unremarkable taxi number. It was 1729. And Ramanujan was like, wait, no. Hardy, you don't understand. That's a beautiful number. It's the smallest number that can be written as the sum of two perfect cubes in two different ways. He just happened to know this, okay? So, do you understand what he said? He said there are two And by the smallest number, we're just referring to like only positive integer solutions to this equation, right? And he's saying this is the smallest number, 1729, that has two unique non-trivial pairs of positive integer solutions, right? And my challenge to you would be right now in the next 30 seconds is see if you can find them, right? Like they're not that hard to find actually, right? Just try a few numbers, see if you get it. Go. He just happened to know this on top of that.
Yeah, 9 and 9.
It's 9 and 10. It's 10 and 9.
All right, so I hear one solution that just popped out. 9 and 10, 9 cubed plus 10 cubed is 1729, is that right? And then what else? And then also 12 and 1, did you catch that? So this is the smallest number that can be expressed as the sum of two perfect cubes in two different ways. 1 cubed plus 12 cubed or 9 cubed plus 10 cubed. And he recognized that amazingly. So that was cool. All right, now that was my interlude. Going back, going back to this. So the reason that made me think of this is because we just looked at this equation right here, x cubed plus y cubed equals 91. The graph of x cubed plus y cubed equals 1729 has almost the exact same shape. Why isn't this a counterexample to what I just said? Isn't this a smaller number, 91, and yet we've just found two solutions? Well, yeah, one of them is negative though, right? So that opens the possibilities a little bit. But the point is, I had to really think hard to come up with this example. I chose 91, not out of thin air. Like I had to think very hard and know that 91 was a value. If you're interested in this kind of an equation that has only integer solutions, no, there's no reason that you can't. Like down here, you answered 1 root 12. I didn't tell you that, but it's interesting that there are even integer solutions at all, right? If you're interested in equations like that, they're called Diophantine equations. We're looking for integer Diophantine equations, and they're it's named for the Greek mathematician Diophantus. Diophantine equations are equations we desire only integer solutions for, and it's actually very difficult to like solve with that constraint. So you take a class maybe in number theory if you want to learn more about that. Okay, if you're looking for like only integer solutions to equations. Okay. Okay, let's then come back together and think about with me, please. Relations and inverses. Again, just like on Thursday, just like on Thursday, I desire to go deeper with you on this subject. Okay? Hopefully on Thursday we met that criteria. We talked about things you had heard about before, but we've gone a little bit more in depth. So that's my plan today, is to talk about something that I assume you already know something about, otherwise this will come too fast for you. If you don't know anything about inverses, that would be a problem. I assume that you already know something about an inverse. But let's also say what they are just to make sure that we're all on the same page. If AB is in a relation, then BA is in the inverse relation, and that's what we mean by inverse, okay? That's like a really formal notion. We could also give it like a real world flavor too, right? You know, think of a inverse of what y is x. Yeah. What about visually? When is it true that the inverse relation will be a function? Just reviewing still some algebra 2 here. Visually speaking, we have like a little cute rule. Something about x equals y. That's actually not what I was thinking, but you're I mean, that's thinking visually though. I like that. So no repeated y values. Yeah, you're gonna say something else now? When it's 1-to-1, if the original relation is a function, then I agree.
Yeah.
Yeah. So I'm just thinking about like, yeah. So I'll take it. Go ahead. X and Y are switched. Okay. So yeah, I'm gonna key in on whoever just said two y values that don't have the same value, right? Or visually speaking, I'm like thinking of like, you know, baby steps here. I'm thinking about the horizontal line steps. Is this ring a bell at all?
Yes.
Like that would be a testing for that. Right? We're just looking for any values that have the same y value, because when we take the inverse, you know what's going to happen. You need to have it be true that the inverse passes a vertical line test. So Okay, so here are a bunch of pictures of relations, and I want to answer both questions. Is this a function first on each one, and then also, if we were to think about its inverse, would it be a function? So please talk with your table and establish the answer going across all four of those. Function, question mark, yes or no, yes or no, yes or no. And then also with your table, answer the question, is the inverse a function? Okay, you get 10 more seconds to fight. All right. Listen. Cameron and company, you guys help me out with this first one here. Which of these are functions? This is just a good algebra 2 review here. Shh, guys, listen. They're about to speak truth. Go.
The first and the last one are both functions.
And the others no?
Yeah.
Okay, so the answer is yes, no, no, yes. Did your table agree?
Yeah.
Okay.
Are we assuming that that's a
Yeah, assume any indicated behavior, please. Yeah. Rachel, lead is you. You guys, your table, talk to me about this question. The inverse of this, would it be a function? Go across and answer that question for each of these. Yes? So, sorry, slow down.
Yes. Yes. No. No.
Do you guys agree with that? Freshmen?
Yes.
Freshman table? Okay. All right.
They're freshmen too.
Yeah, true. I know.
No, we're not.
All right. Is that good? Is that good? All we're doing here to answer the first question is asking, does it pass the vertical line test? Yes or no. And for the second question, does it pass the horizontal line test? Yes or no. Right? Just to be clear. Okay. I don't have anything else to say about that right there. Why is this not working? Okay, we want to talk about this notion someone already mentioned of one-to-one-ness. So we've only been focusing so far on really talking about like inverses in terms of relations, but we want to like think about when a function has an inverse that's a function, right? And this is what Noah said earlier, right? This is the notion of it has to be a one-to-one function. It would have to pass the vertical and horizontal line test. So which one of the ones on the previous slide would have done that? Which would have been a one-to-one function? The first one only, right, was one that was both a function and had as its inverse a function. So, you know, just in the wild, in general, it's not necessarily true that we have functions that are invertible, right? Just want to make sure you're clear on that. Yeah, so there it is, right? Not all functions have inverses that are functions. Let's just make sure that we're clear on that. If we were to go back to like the definition of a function, algebra 1, for every input there is exactly one output. So we also add the condition here though, that for every output, there's only one input, right? Okay, so here's another one for you to try with your table. And I'm going to tell you to do it with your table because I think that you're going to maybe struggle with it, even though I know you've found inverses before. But I think this algebra might be a little tricky. Try it. That's t over t plus 1. Okay, so you can find the inverse. Check with your friends. And say what the domain and range of f inverse is, too, please, if you will. You can do that.
You can't read any. All that matters.
Help each other out.
It must be.
Well, it works. You know what you might what did you get?
Tell me if your table gets it, because I'm not.
I got it. X equals y squared. Okay, so I got y squared, and then I can get the square. Oh, got it. Y equals square root of x. That should not happen, should it?
Wait. I write, if I go and change that means the y side.
Here, let me test
You get x over 1 times 1 over y is 1 over y. And this y. X over y times y. Times y. I multiply by 7. Stop making it too complicated.
I was lying. What the heck happened?
Good.
Multiply both sides by 2.
No.
So you multiply both sides by 1. X, y. Then you can divide the x out of 4. Yeah, then you get
All this propulsion just sounds like such a bad.
oh my gosh. Wait, I already know what the opposite.
All right, someone, help us.
This is homework number 5.
Anyone?
It's
Don't make me do the algebra. Someone, you. You got it?
oh, it's 1 over x.
All right, Rose.
It's 1 over x. Okay, well,
That's right.
okay.
There's something on this like I have T times.
I think it's 1 over x. Where?
You're not actually.
I think it's 1 over. Oh, it's plus 1. I think it's 1 over x. It's 1 over x plus 1, right?
Yeah, but I don't know how to get
I don't know how I get there either, but it makes sense.
Y times.
It's 1 over x, right? Yes, it is. What?
I did Google Sky last night and similar problem and it is 1 over x plus 1. Or x
I knew it.
it was 1 over
Okay, let's come to order. Thank you, Rosie, for putting the answer up here. Okay, the inverse you should get is F inverse, we might call it, I guess.
Oh, please don't use us.
F inverse of t is equal to t over 1 minus t is what you should have gotten. okay? The algebra's up here, right? Let's take a little play-by-play. You switch t and y. I might challenge you to think hard about like why you do that or whether that's even appropriate to do, but let's go with it. Okay. Over here, you multiply both sides. Looks like a y plus 1, which is not a huge surprise. I think most people did that. Good job. All right, keep with it, though. Move everything that has a y over to one side. Factor the y out, right? And then you're home free, okay? You see it? You see it? Okay, so there's the inverse. F inverse, I'll write it one more time over here. F inverse of t equals t over t, 1 minus t. Sorry.
I got you.
All right, wait. We're not quite done yet. We also need to say, listen, what is the domain and the range of this function of f inverse? What's the domain and what's the range? We should say it. Yeah, wait, let's see here. Let's start with, I don't know which one you want to start with. How about domain first? What's the domain of this guy, f inverse? Everything but 1, right? The domain is anything but 1. Good. And what's the range? That's a little bit harder to see maybe. I don't know. But up here, we kind of glossed over this point here. I just kind of raced ahead and asked you to find this inverse. So let's pause and make sure we understand. If a function is 1-to-1 f, then it has inverse f inverse with domain R and range D corresponding to D and R in the first sentence. Okay? You with me on that? So what if we know the domain or the range of the original function, then we also know the range and the domain of the inverse. So what is the domain of f? Anything, yeah, not equal to -1. So here, if you want to call it y, I guess, y can't be -1, right? That's one way to think that through. If you know stuff about like what that graph looks like too, if you already remember some things about rational functions, we'll talk more about rational functions soon, but then you might also know about that. Yeah. Yeah. Yep. Right. The range of this is everything but 1. Absolutely. No. The range of the original function is all numbers but 1. Right. So this will never output the number 1, the original function. Okay. All right. What am I going to put on this slide? Someone refresh my memory. Another fun fact about inverses. Yeah. Yeah. There's a reflection over the line y equals x that produces the inverse. Here's a picture of y equals x squared for non-negative values, and then also a picture of the square root function in purple. And there's the line y equals x. I'll put $1 on the following problem. First person to bring me a formal proof of the fact that AB and BA are reflections of each other over the line y equals x. Like using geometry, like formal argument. Prove that the line y equals x is actually the line of reflection for AB and BA. It takes like some serious geometry work, right? Like what does it mean for a line to be a reflection line for 2 points? Right? No, it's just for fun. I'm just saying, people tell you these things, but see if you can like prove them. It'll take you a little while. No, like bring it to me later, all right? It's not gonna take you a while. If you already have it, then you didn't do it right. All right, find the inverse of this guy.
How many steps does it normally take?
Wait, but BA will equal the same value.
All right, let me give you another minute here just to find the inverse of this. Go. Give people some silence as they find the inverse. When you're done, just do like a pencil drop, an audible pencil drop when you're done with this. Okay? When you're done.
Why 91?
Are you done? No. Don't drop the pencil, please. Don't give it away to anyone.
You shouldn't have done this.
When you're done, make it, it's yeah, because it's exciting too. I think you'll find this to be actually kind of more thrilling than the other stuff. Right? Remember, right? That it's a little bit thrilling?
Oh yeah.
Drop that. tell you the answer in 10 seconds, whether you've got it or not. So you can get it on your own before study. All right. The answer is what?
X cubed plus y cubed equals 91.
No. What's the inverse? What's the inverse? What is the inverse? What is the inverse? Somebody. What is it? The exact same thing. Yes. By the way, this should look a little bit familiar. Am I right? Okay. Stop. Stop talking. Stop talking. I wanna ask you why we maybe expected this. If this is the picture.
Oh.
Why is it its own inverse?
Oh, the idiots that have symmetry over the
Can you think of any other functions that are their own inverse? Alright, come on. Homework 5. Homework 5 tonight, please.